uh, giving you the state-of-the-art of particle physics, and at the same time, including a sort of introduction to what particle physics are and the methods of particle physics, particularly since it is expected that more than half of you come more from an astro background than from a particle background. And so I'm bound to fail because I won't be able to do everything. And as a result, I'm going to probably go too fast for some who need an introduction and too slow for some who don't. And hope to make you all equally miserable. Just democracy. Also, I have to apologize for not including any jokes in my lectures. I like to do that. I just didn't have time. It was prepared in short notice. But anyway, I'm very glad to be here. I've come to La Laguna many times, and I've never actually been in this building. So when you hear these little kids running around the back, one of them might be me. Sorry about that. So particle physics on a leg means that we're going to stand on a leg and teach you all of particle physics. And so let's just get going. There's not much time left. Here's the content over 2 lectures. And so as you can see, I'm going to do, as I promised, an overview of a lot of the very basic tools of particle physics. And then I'm going to go into some other things that I would expect even some of these students that come from particle physics and theory might not know about it. And it's all tried to done really mostly qualitatively so that you can develop the language to talk about these things. In order to develop the quantitative knowledge to master quantum field theory, or for example, monopoles, you need 1-year course on each. And we have 50 minutes twice. But the goal is not that. The goal is that you can talk to other people and understand and have a fruitful discussion scientifically. So let's just get going. So I'm going to be using units in which the speed of light is 1. So Einstein's the most famous equation in physics is just E equal m. And so therefore mass and momentum is all measured in electron volts, which you think of as a unit of energy, but it's actually a unit of momentum and of mass. And really in particle physics, electron volts is too small a unit, so the standard is to use giga electron volts, or 10 to the 9 electron volts. And if you wonder what that means, about 1 proton mass. And one exercise for you is to look up the actual mass of the proton in GeVs. It's a little bit less than 1. And you might want to also look at other standard particles and see what their masses are in these units. I'm sure you might know them in grams or kilograms or something like that. I also use h bar equal to 1. This is fairly standard in particle physics. So energy is also h bar omega, which means E is equal to omega. So frequency is measured also in units of electron volts or giga electron volts. And of course, wave vectors like k are also measured in units of what you think is momentum, but again, it's just GeV. And because you think of wave vectors as inverse lengths, lengths are measured in units of 1 over GeV. And since speed of light is 1, time is measured in units of 1 over GeV. So how to go from usual length measures to GeVs? So the one thing that every particle physicist know, and I'm looking at some particle physicists, no, I don't know that, but you should. 1 Fermi, which is about the size of a nucleus, is 10 to minus 15 meters by definition. And that's around 1 over 200 MeV, or 1 over 0.2 GeV. So special relativity, which everybody here is familiar with, the metric is, of course, proper time and proper length are in the same units because c is equal to 1, so I'm not going to make a distinction. And then the metric, I use the plus, minus, minus, minus convention, and g mu nu is used to denote the metric, but sometimes I use eta mu nu, particularly when we're in flat space. Okay, so that's just conventions. Quantum field theory. As I said, after 2 years of quantum field theory, you don't become an expert. It takes a lot of work. But let me start with why do we need it? So if you look at the regime of different areas of physics as a function of typical energy of the process under investigation, the few electron volts type transitions are what you associate with atomic physics, right? And typical electrons. So if you look at those energies compared to the mass of the electron, you get a gamma factor, which is 1. Or the beta is very small. That means it's non-relativistic physics. And you know that from your first course in quantum mechanics. When you go up to around an MeV, a million electron volts for energies in transitions, you're in the realm of nuclear physics. And in nuclear physics, you're still most of the time talking about non-relativistic physics because although I wrote here E over m of the electron, for nuclear physics, of course, you talk about the energy over the mass of the neutron or the proton. And so the beta factor is small, gamma is 1, it's non-relativistic. But in both of these cases, you clearly require quantum physics. The realm of particle physics is, as I said, GeV and above. And then the gamma factors for any particle become bigger than 1, meaning it's relativistic physics. So you need to marry special relativity and quantum mechanics. And the only way which we know to do that is through what we call quantum field theory. So that's what quantum field theory is. And why do we talk about it here? I told you in the introduction, it's the language of particle physics. And so what is it? It's the description of elementary particles and their forces. And this is done in quantum field theory through fields. So the fields are the fields like the one of the photon that you're familiar with, of the electromagnetic field, which I don't have to remind you of. But what's different is that, and you may or may not be familiar with this, is that the fields themselves are operators in quantum mechanics sense. So if you've done studies of second quantization, that's what second quantization is about. A is an operator, and then the states on which those operators act, those are the particle states or multi-particle states. So for example, I hope you can see these colors. I thought it was really cool when I was writing this, but now, can you? Otherwise, I can tell you a great story. Right? So here's a photon. A photon has momentum. It's characterized by two things, momentum and spin, or instead of spin, you can use its polarization. And so roughly in quantum field theory, you take a state, which we call the vacuum state, in which there's no particles. And then you take this, the field, which is now an operator, quantum mechanical operator, acting on this state of no particles. And to make it have definite momentum, you make a momentum decomposition, which is a Fourier transform, which is what I've done here. And to pick up a particular polarization, you choose a combination of the little directions of the vector. And then this whole thing is basically the same as the photon field, roughly. There's a little bit more detail that I'm skipping, but that's the essence of the idea. Notice that X is just a label here. It's not an operator that is used in quantum mechanics. The operator that we have is itself the vector field A. So that's what quantum field theory is. Done. Now, we use it in many ways, and one of the things that I wanted to introduce very, very quickly is the language of Feynman diagrams. You might have seen them, you might not, but we're not going to try to learn how to compute with them, But I want you to make sure that if you look at one, you know what it means and what is involved. So one thing you do know from learning quantum mechanics in kindergarten is how to do perturbation theory, right? So if you have a perturbation to have some exact eigenstates of your Hamiltonian, and then you introduce a perturbation, then we're going to call it H sub int for interaction. And you want to know, sorry, so your states are labeled by these n, but one particular state, say psi, and I want to see how much that state is changed by the presence of that new interaction. And you know how to do that. You do that with perturbation theory. That's the theory that you learned also in school on how to find, at first order in perturbation theory, the change in the state psi. And there's a counterpart for this in solving quantum field theories perturbatively. And then that counterpart can be nicely represented in terms of pictures. And that's what Feynman diagrams is. So in this expression that you're familiar with, there's a denominator, which we call a propagator, and involves energy differences. And in the numerator, there's a matrix element here of the interaction Hamiltonian, and we call that a vertex. And to show you how that works in Feynman diagrams in quantum field theory, the representation, this pictorial representation of a scattering amplitude, for example, E plus E minus going to mu plus mu minus, you have here a picture, time goes left to right. And what this picture says is there's an electron going in and a positron going in, and the arrows mean something, which I'll mention very briefly. And then there's and I reversed, this arrow is incorrect, should be pointing the other way, but a muon going out and an anti-muon also going out. So it's E plus E minus into mu plus mu minus. And in this process, what we see is physically, you think of the electrons as annihilating into a photon, but this photon is not a real state. It just represents this type of propagator. And I'll show you this on the right-hand side in a second. And then this photon, quote unquote, becomes a muon, an anti-muon pair. So that's a useful way to think about physically what's happening. But really, this means an expression just like up here. And this photon line, and this line inside the diagram, stands for 1 over some quantity. This PE plus PE bar is the sum of the 4 momenta of these particles coming in, quantity square, and it actually stands for the same thing as this propagator. One can show there's a one-to-one correspondence. And then these external lines correspond, just denote these particles coming in and out, and then these vertices here correspond to these matrix elements. This is actually second-order perturbation theory where you have 2 vertices coming in with one energy denominator. So this is one of the vertices, this is the other vertex, and as I said, I'm not going to tell you exactly how to compute it. Let me just go on. So how is this able to convey some useful information? Even if you don't know how to compute it in detail, notice that the thing that I wrote down had a photon labeled in this internal squiggly line, which is this propagator. But if I label it as a Z node, the Z node is a particle of the electroweak theory. It's a Z boson, which has a mass of about 90 GeV. And this same type of diagram with the same internal in and out states now depicts a weak process because it's a weak vector boson that is mediating interaction. Another type of information that this gives you is that this diagram is the lowest possible order in perturbation theory for which you can get E plus E minus going to mu plus mu minus type diagram. But you can also write something like this. You can see the rules allow it. And this is a correction to the previous order, which is smaller. Each one of these dots involves a factor of the coupling constant, or some number that characterizes the strength of the interaction. So this diagram is proportional to E squared. This appears 4 times here, so this is proportional to E to the 4th. And E, of course, is the coupling constant of electromagnetism that you're familiar with. So E squared over 4 pi in my units in which h bar c is equal to 1 is 1 over 137, the fine structure constant. That's it. So how do we actually build these theories? One of the most important precepts in constructing theories of forces of elementary particles is gauge invariance. And so gauge invariance is something you're familiar with from electromagnetism. Here's Maxwell's equations. Well, not quite. Here's the electric field and magnetic field in terms of a scalar, the electrostatic potential, but it's not electrostatic because now we have dynamics, and the vector potential, so the scalar and vector potentials. And you know from, just from looking at this actually, but from electrodynamic courses you've had, that these fields E and B, electric and magnetic fields, are invariant under the shift of the scalar potential by a time derivative and the vector potential by a gradient of a single function of space and time. In covariant form, you can have a covariant form of these equations, which you hopefully also have already seen. Since you do astrophysics or you do particle physics, you deal with general relativity, so you know this formalism, in which the scalar potential is the 0th component of a 4th vector. And then the fields E and B are part of a antisymmetric tensor field. And then the gauge invariance is very simple. It just means that A mu, the 4 vector, is shifted by the 4 derivative of a scalar field. Okay, and in quantum mechanics, you also know how this works. The electron wave function, which satisfies Schrodinger's equation. Well, this is the time-independent version, which serves is enough for me for now. To introduce its electrodynamics into that theory, you do minimal substitution. You replace the gradient by this combination with the vector potential. And you do this so that under the transformation of this wave function by a phase, by an arbitrary phase, omega is an arbitrary function of space and time, that this whole combination that you introduce now transforms exactly the same way by a phase. And the only way this can happen, of course, is that if at the time that you make this transformation of the wave function, the field A transforms by the same gauge transformation that I showed in the previous page. And so this combination is called a covariant derivative. And in field theory, what we do is exactly the same thing, except that instead of thinking of the electron as described by a wave function, we introduce an electron field. And again, electron states are created by this field, just like I showed photons are created by the photon field. And so you have many, many electrons created by the same field, just by applying it many times to the empty state. And this field, this operator on the Hilbert space, satisfies a Dirac equation, which, by the way, we write as d slash gamma mu d mu, where gamma mu is a Dirac matrices that you know of, is replaced just by d slash for short. And gauge invariance means that you can make this equation invariant under a change of the field by a phase, provided I replace this derivative by the covariant derivative, just like before. And now I put an extra 0th component to make it all covariant under Lorentz transformations. So this is how gauge invariance is useful, that it allows us to find a technique for taking, for introducing interactions of vector fields with any kind of particle. So here's what quantum electrodynamics is. First of all, it's a field theory, and to describe the dynamics of fields, we always do this through Lagrangian densities. And so Lagrangian density is built out of, for example, these fields A mu for the photon and psi for the electron. And then we imposed on this Lagrangian density a number of symmetries. So if you want your theory, your equations of motion that the fields have to satisfy to be covariant, for example, you demand that the Lagrangian density be invariant under Lorentz transformations. But then we also impose that the Lagrangian density be invariant under gauge transformations. And at first that was from experience. That's how electrodynamics works. In the end, it turns out that in order to demonstrate that these theories are mathematically consistent, we need gauge invariance. So extensions of quantum electrodynamics to other forces are based on gauge invariant theories because that's the only way we know how to build a consistent theory. So to make a gauge invariant theory, you just use F mu nu, which is an invariant in constructing your Lagrangian, and covariant derivatives when you have derivatives acting on the electron field. And so here's what you can write down. The lowest order, the simplest Lagrangian density, which is invariant under gauge transformations and Lorentz transformations, is something like the square of the field strength, which you know in electromagnetism as E squared minus B squared. And this factor of -1/4 is there so that it actually is 1/2 E squared minus B squared, precisely what you know it should be. And then this term, well, these two terms together, give rise to the Dirac equation. When you make a variation of the Lagrangian using Euler equations to find equations of motion, this gives you the I gamma mu d mu minus m acting on psi equal to 0. That's it. This is the famous Lagrangian for which Schwinger, Tomonaga, and Feynman got a Nobel Prize for showing that it does define a consistent theory mathematically. But the reason we're introducing it here is that we want to talk about generalizations, and this is where things get interesting for us, because I'm sure that a lot of these you've seen in one guise or the other. But one thing you can do is say, well, instead of having a single electron field, I'm going to have some sort of field which has many components. Here's a field with n components, like a vector type thing that I organized in a column. And then when I make a transformation that I want the theory to be invariant under, I transform by, well, I want it to be e to the I some phase, but now because I have a vector here, I can have the phase act differently on the different components here, right? So I'm going to multiply multiply the phase by a matrix. And in fact, because I can have different choices of the matrix, I'm going to label these things with an integer a, and there's an implicit sum on a, meaning that I really have kind of different gauge transformations depending on these different parameters, omega, and the corresponding different matrices. There's an overall factor in front g, just like there was an e, which is going to be called the coupling constant. And it will turn out to be important that just like a phase is unimodular, the modulus of a phase is 1, that this thing, which is now a matrix, because it's acting on this thing, which is a big column, that this combination, which I'm going to call U, because it's label for the whole matrix, is unitary, which is the statement that the inverse of the matrix is just the Hermitian conjugate. This is exactly the same thing as being unimodular, but in terms of matrices now. So that's the generalization. In order for these matrices to be unimodular, if these parameters are real, g and omega, and here we have an I, which is purely imaginary, the requirement is that these matrices T be Hermitian. Okay. Now, you're going to see me use SUN a lot. You might have been introduced to this set of all n by n matrices, these things U that I introduced, that are unitary, U dagger equal 1, and have determinant equal to 1. That's an additional restriction that I didn't have in the previous slide, but now I'm introducing it. That said, it forms a group. And that group is called the special unitary group of n by n matrices, but just SUN is good enough for us, for anyone. So we're going to take these matrices to be in that group. And for that thing that I wrote down, this exponential, to be a member of that group, it's required that these matrices that I wrote in satisfy a commutation relation. That's just there so that the product of two matrices are still in the group. And one can show that. But let's not bother with the mathematical details. These F, A, B, C are a set of numbers that are fixed once and for all. They kind of characterize the group, actually. They're very important. They're called the structure constants. But this is not we don't want to go into details of group theory. This is called a Lie algebra, by the way, in case you come across that. So here are a couple of facts. I'll give an example in a second, but here's a couple of facts. You can always choose a basis for these matrices such that the trace of a product of them is 0 if they're different matrices, and it's normalized to anything you want, so that the trace of the square is, for example, 1. So mathematicians take the trace of the square of a matrix to be 1, and physicists take it to be 1/2. And that's because we're really cool. No, I'll explain why we do that in a second. It's historical, but it's curious. And another thing which is kind of interesting for SUN, or useful, I guess, another fact, there's this basis of matrices is n squared minus 1 dimensional. So here's an example, SU2, 2 by 2 unimodular matrices. You probably saw something like this in your courses on quantum mechanics. The matrices, these matrices TA, but they're called generators. I should have mentioned that. These generators of SU2, these matrices TA, they're actually just the Pauli matrices that you know of. You don't remember the Pauli matrices? Here they are. And so they're characterized by having a commutation relation, right? Sigma, these T's are sigmas now, right? So 1/2 the sigmas. And you don't know, the commutation of sigma matrices is I epsilon, a Pauli matrix. And you know that the trace of a product of them is 0 if they're sigma 1 times sigma 2 is sigma 3, for example, and all of them are traceless. So the trace of the product of 2 is 0, unless you take the square. And the square of any one of these matrices is the unit matrix. And the trace of the unit matrix is 2 in 2 dimensions. And the reason we introduced this convention that the traces are equal to 1/2 something is historical. Is that all the matrices were used for spin, of spin and half particles. So we wanted to put a 1/2 here so that the entries here are 1/2 everywhere, right? Like 1/2 and minus 1/2 historically. So the eigenstates have eigenvalues 1/2 and minus 1/2, which is what we think of as spin. And the trace of those matrices with the 1/2 have this overall 1/2. And then we decided in particle physics, or in physics in general, that 1/2 is very good for any SUN. So that's what we do. But that's an example. I hope that sheds some light. We'll see other examples later. So let's continue with our generalization. The covariant derivative now, since psi is transformed into a matrix times psi, we want the covariant derivative on psi to also transform the same way, just by a matrix. And the solution should be no surprise. It's the same as before. We shift the derivative by a term, which involves, instead of this omega that we have here, we replace that with a new vector field. And this vector field, notice there's one for each A, and there's a sum implicit again. These are called gauge fields, and there's n squared minus 1 of them. So for SU2, if you make a gauge theory based on SU2, there's 3 gauge fields, not just one that we have in electrodynamics. And so the last step is, and this is a little bit more technical, so I'll do it quickly, just try to get the gist of it. we need some sort of field strength to construct the full Lagrangian density. We know how to construct the density now for these fermion fields. Just have a covariant derivative, same story as before. But for the fields, we'd like to do something like this field strength. And you need one for each one of these n squared minus 1 gauge fields. And it turns out that a simple way of, well, let me first organize them into matrices. So we have each one of those multiplied by TA, sum of rate, gives you a matrix. And the reason this is useful is that if you compute the commutator of two covariant derivatives, that looks like an awful thing. But it turns out this is not a derivative operator because the derivative part of this cancels in the commutation. So this is just actually a field. And the way I've written it, since this derivative transforms just with having one of these U matrix on the left, you can show very easily that this transforms so that this matrix F under a gauge transformation is not invariant, but it transforms via this unitary matrix on the left and on the right, UF, U inverse, or U dagger. So that if you take the square as before, the square also transforms like U, F square, U dagger, or U inverse. And if you take the trace and use the cyclicity of a trace, this is invariant. So that's the Lagrangian density. As I said, it's a little technical, and you don't really have to, not at this point in great detail, but this is how we do it. And there's a 1/2 here because there's the extra 1/2 in the definition of the trace of the square of T, of these matrices T, which give you the usual 1/4 that you saw in electrodynamics. So that's a gauge invariant Lagrangian. So now you can write down, for example, this is the gauge invariant Lagrangian for the gauge fields, and this is the one for the fermions. And of course, there's an interaction here because this derivative includes a term which has a product of the gauge field and the two fermions. So let me tell you how these are building blocks for Feynman diagrams without deriving anything. I'm just telling you, right? So first of all, if you look at the quadratic part of these terms in the Lagrangian that are quadratic in the fields, give you these internal lines that I call propagators. So I'm not giving you what the lines actually stand for in terms of numbers. But I'm telling you that there's going to be a line like this, which we have with an arrow, which stands for some internal line having to do with the fermion field. And a squiggly line like this, one for each one of these gauge fields. And we usually put a label A and B here, meaning this is the gauge field A. Remember, there's n squared minus 1 of them. And this is the gauge field B. And in this line, actually, A has to be equal to B. There's a delta AB, if you want, with a Kronecker delta. And then, as I said, there's a term here which has a gauge field and two fermions. And from that, in your diagrams, you're going to see things like these, where there's a fermion line going in, a fermion line going out, standing for one is for psi, one is psi bar, and then there's a gauge field A. And it's interesting that so this is very much like in electrodynamics, except that now there's many more indices that we didn't have before, meaning things like, there's 3 gauge bosons in SU2, and the gauge bosons can change one component in the vector field for another component of the vector field, because that's what these matrices do. And we'll see some examples later. But one of the interesting things here is that these fields, these field strands are not linear each in the gauge field. And this term introduces self-interaction of the gauge field. So there's something that we don't have in electrodynamics and you're not familiar with unless you've done studies of these theories, which are called Yang-Mills theories. There's contributions in which physically you can think of 2 gauge fields coming in and annihilating into a third one, or 2 gauge fields coming in scattering into 2 other gauge fields. So this is new. This is something that happens in Yang-Mills. As I said, regardless of the formalism that got us there, which is nice to understand and so on, it's important for you to understand this language and what it contains. Okay. One of the things that that happens in those Lagrangians that I wrote down is that all of these gauge fields are masses. And in order to get masses in those gauge fields, you need to introduce this phenomenon of spontaneous symmetry breaking. And this will actually play a role in a lot of other stuff, not just here. So, for example, for inflationary models, you need to understand spontaneous symmetry breaking. So let me do a version of this model that we were talking about, electrodynamics, but with a scalar field. A scalar field, well, this is not the physics that we know of, but we play a lot with this kind of stuff in particle physics, where we introduce models that are putative models of nature, but are really just toy models to understand how dynamics works. And so a scalar field is a spin zero object. Don't confuse this with the scalar potential of electrodynamics. Scalar potential of electrodynamics is the zeroth component of a 4-vector. This is an independent field by itself. It's just a field that has no transformations under Lorentz boosts, for example, or rotations. And so in the absence of interactions with the electric field, this would just be the covariant derivative of phi magnitude square, the derivative of phi magnitude square. But if we want phi to transform by a phase under a gauge transformation, then you turn the derivative of phi into a covariant derivative, just like before. So that Lagrangian that I wrote here is an invariant Lagrangian. And now notice that I introduce now here a function of the field. And I make the function of the field one on the modulus of the field, or the square of the modulus, so that it's invariant automatically under these gauge transformations. And this potential is what we're going to be paying attention to. So here's an example of a potential that we use quite a bit. It's called, it has a quadratic terms in the fields, or you go to the modulus square, and this is the square of the modulus here. Okay. And we take this constant lambda to be positive so that the energy, the potential is an energy, stays positive when the field gets arbitrarily large. Mu square, although it's called mu square, it can be positive, it can be negative. It's just the name of a parameter. It's very confusing when you first see this, because how can mu square be negative? But mu square is just a name for a parameter. Could just call it Peter or Mary or something. Just as good. And if mu square is positive, then think of this as a function of the real part of phi for now. Think of phi as real. It would be a function that just looks like this. It starts quadratic here and then becomes quartic. And clearly the minimum is at the origin. But if mu square is negative, then the form of this function is very different. It's quadratic close to the origin, but with negative curvature. But then because lambda is positive, as phi gets large, it tricks off and becomes positive. And what happens is that you develop two minima away from the origin. And this minima you can compute is just, the order of minus mu squared over lambda. It's a 2 if you take a derivative and compute. It's not a big deal. Of course, this is not a real field. It's a complex field. So if I write now, here's the same picture, but instead of just looking at a cut, when I look only at the real component of phi, have a plane here, which is complex phi. So this is real and imaginary parts of phi. And it's symmetric on revolution around the vertical axis. So the previous slide here, if you take this thing and rotate along the vertical axis, you get a surface like this. Its minimum is still here at the bottom, right? Whereas for the other one, what happens if you rotate it is that those two minima make a circle. I think I say this somewhere else, but this is often called, there's two names for this. You'll see in the literature. One makes me very proud to be a Mexican. It's a Mexican hat potential, if you can imagine it. I don't know. Well, it's like a sombrero potential. That's a charro. Okay. The other thing is a bottom of the wine bottle potential. And this reflects habits of physicists late at night. Now, here's what happens, which is kind of interesting. If you want to try to understand how to do physics with these potentials, you take your field at the bottom, at the bottom of that circle, and say, well, the minimum possible energy configuration is when the field is all equal to some value somewhere around the circle. So, for example, let me choose it to be here, meaning like there. Right? If I take the field to be some function that in space changes as you go around the circle, even though you're at the minimum of the potential, these derivatives here contribute to the energy, and that gives you higher energy. I'll come back to that tomorrow when we talk about solitons. So if you want to be really at the minimum of energy, you have to choose a particular point, no matter which, because they're all connected by gauge by invariance. You can go from one to another by a phase transformation, and the phase and invariance of the theory, you get the same energy. They're completely equivalent. However, you notice something kind of interesting. If you move around, if you take the field and say, let me make perturbations around it in this direction, like I introduced here, this looks like, it looks actually like this picture again. And this actually corresponds to a massive field. The energy gets increased as you move away from the center. And in fact, you can compute that the mass of that oscillation, of that, oscillations in quantum physics become quantized, and those quanta correspond to masses in field theory. So the second derivative of the potential with respect to that direction, that gives you the mass. But if you move in this direction, this is completely flat. It doesn't change the energy. And that tells you that there's a massless mode. So there's a particle which is massless. And something interesting happens, and again, I just have to tell you what happens without proving it. If you don't introduce gauge interactions, although I have them here, I could do the same thing without this gauge interaction and just a normal derivative here, just d mu. You would have a massless particle. So this guarantees that this model describes a massless particle, and it's called a Goldstone boson. But if your theory is gauged, like this is the case in this example, then we have something which is very peculiar. This thing that looks like a massless particle, because there will be no change in energy as you move around, doesn't exist in the theory at all. It disappears. We say the particle is eaten. It's like a nightmare for children, but like the children are going to be running around the back. But it's eaten in the sense that a vector field, the vector field associated with this gauge symmetry, which you thought about it as a photon originally, photon with two polarizations, right? Becomes massive also. It acquires a mass, and then it turns out a massive spin 1 particle, well, spin 1 has 3 degrees of freedom. It's curious that the photon, which is spin 1, has 2 degrees of freedom, but that's because of gauge invariance. But here what happens is the gauge invariance is, we say it's spontaneously broken because you chose a specific minimum to expand about this. There's no explicit gauge invariance. It's kind of hidden in the back. And as a result, the photon becomes massive, and 1 degree of freedom that you need for a massive particle, that 3rd degree of freedom, actually is supplied by this would-be Goldstone boson, this particle that would be there but is no longer there. And that's actually a technical term, by the way. Would-be Goldstone boson is a technical term in the literature. So that's the phenomenon of spontaneous symmetry breaking. The mechanism is now called the Brout-Engler-Higgs mechanism. And this gentleman got the Nobel Prize in 2013 for this work. And the massive mode that you get, this mode that you get here, this massive mode, this one, which is massive, is called the Higgs particle. And you can actually kind of see how these things work explicitly without a lot of work. If you take the minimum, this is fairly standard notation. They know the minimum as 5 with kind of an expectation value. And you say that this is a number. Let's take it to be real. It can be anywhere on that axis, in that circle. So you can take it to real, on the positive real axis. So take it to be v equal to some number v positive. Expand the Lagrangian L about that term. So take the scalar to be v plus some small perturbation. And then you look at the derivative d mu phi, has this covariant derivative. Notice there's a term a mu times v. So when you square that, there's going to be a term a squared times v squared times, of course, there's an e squared. So this quadratic term in the field gives you the mass in quantum field theory for the particle. And you can see that the new photon mass is related to the expectation value of the field and this quantity e squared. So that's how you derive the mass of the field in the spontaneous symmetry breaking case. And it's not very difficult to show that the phase the phase of this perturbation doesn't contribute to anything. It just goes away. It disappears from the Lagrangian. Okay, so let me spend a couple of minutes talking about discrete symmetries, and then I'll stop and I'll do the rest of the lecture tomorrow. So CPT, there's 3 discrete transformations that are going to be very interesting. And the question is whether they are symmetries. And you know about them from quantum mechanics, probably. But there's a version of them in quantum field theory. Actually, in quantum mechanics, this is not so familiar. The other 2 are. So charge conjugation, it takes particles into antiparticles. So a charge conjugation takes an electron into a positron and vice versa, a muon into an anti-muon and vice versa, and the photon into a photon, because photon is a real particle. It's its own antiparticle. Parity you know of from elementary courses. It takes space into its mirror image, and then the momentum is also mirrored. And then there's some pseudo vectors like the angular momentum, which don't change, because as r cross p, there's 2 minus signs, right? And time reversal, again, takes time into minus time, so space doesn't change, but momentum, which is a time derivative, does flip. So in quantum field theory, there's a Lagrangian density version of this. And the question that we want to ask is whether the Lagrangian is unchanged under them. So, so charge conjugation takes a field, for example, the scalar field that I just showed in the previous example, into this complex conjugate. And you can kind of see why that is the case, because if I take the field which transforms via a gauge transformation like this, you take the complex conjugate on both sides, notice there's a minus sign here. It's like changing E into minus E. So it's like changing its charge sign. So it's a simple version of charge conjugation for any kind of field and any kind of gauge transformation that you want. Parity, of course, is very simple. You take x into minus x as the argument of the field. But there's something else that can happen. You can also switch the sign of the field. And that defines different versions of the transformation. And you have to check all of them to see if one of them makes the Lagrangian invariant. Right? So for example, you know that vectors transform odd. There's an odd, there's a minus sign for a vector, and there's a, for angular momentum, there was no minus sign. So those defines, there's vectors and they're axial vectors. So there's scalars and there's pseudo-scalars. And there's a version for this for fermions that I'm not writing down. But it's interesting that you can write down these spin-and-a-half particles there's into a spin which is right-handed, so the spin goes this way, and left-handed, if the motion is this way, it's rotating that way. Left-handed meaning it's rotating in the opposite direction. And you can extract those, you can decompose a field into the 2 components. And parity actually switches left-handed with right-handed, so it's not a big surprise. And time reverse I'm not going to explain because it's an anti-unitary transformation, but you've seen that in quantum mechanics courses, and it's kind of complicated. But but it does the obvious thing. It changes time into minus time, and you can, again, have both signs here. And so I'm going to finish with this slide and just skip the next one. There's a couple of interesting, really interesting combinations. CPT, so acting with C, then P, then T, actually in any order. It's really interesting because it's always a symmetry, provided you're talking about a quantum field theory, and the quantum field theory is Lorentz invariant, which is usually what we do. And the Hamiltonian is Hermitian, in other words, preserves probability. So if your theory preserves probability is Lorentz invariant and is based on quantum field theory, it's simultaneously automatically invariant under CP and T. The combination CPT, not CP and T, sorry. And then the product CP is particularly interesting because it can always be defined. And for CP to be invariant, the couplings in the Lagrangian have to be real. And this is going to be playing a little bit of a role when we talk later on about baryogenesis. This is why I bring it up. And checking that CP is violating is a huge part of particle physics. It's a huge field in checking whether CP. It's very well established that CP is violated. I had this somewhere later. It comes later. It's violated in weak interactions of hadrons. And it's believed to be violated in neutrino oscillations, but it's still not completely determined. So it's something which is an ongoing part of investigation. So I think I'm going to stop there. And there's maybe time for questions.
Any question in the room? There I go.
Hello.
Hi.
Can you please give me an example of one event of a potential with double minimals far away of the center? Because you say that this is correspond to the less massive regimen. And I was thinking in a binary star system that they are rotating, and so they can create this potential. But I don't know if the potential that you show me just correspond to the particle regimen, or also in the high mass regimen. I don't know if I understand correctly.
Yeah, that's a very good question. So the potential that you're thinking of in a binary star system is a gravitational potential that arises, between two massive objects that are separated, and it reflects the dynamics of the gravitational interaction between particles. What it actually is measuring, that potential, is the energy as a function of distance between two clumps of mass. Right? Now, this potential is different. We call it a potential because it plays, when you construct a Lagrangian, you usually say it's T minus V, where T is the kinetic term and V is the potential. And the kinetic term is the one that has time derivatives, and then the potential is the rest of the Lagrangian, or minus the rest of the Lagrangian. And so that terminology went into designing these Lagrangian densities for quantum field theory. I think tomorrow I'm going to write down an expression that shows you the actual energy in a configuration of fields as a function of the fields. And there's actually two terms. There's one term which is this function that we call the potential. And there's another term which is a derivative term, which has spatial derivatives. And it does actually measure energy in the sense that the energy of a configuration of the field itself does have some energy. But it's very different from the energy of, say, a collection of, if I wanted to ask the question, what is the energy for a collection of particles, and maybe two lumps of particles, that potential energy, that potential function, if you want, would play a subsidiary role in that it would tell me something about the description of the field that connects those lumps of masses, for example. But it wouldn't directly give me the potential energy. So the two quantities that we're talking about are very different. I hope that makes some sense. Yeah.
Yep. Thank you, Benjamin, for the talk. And regarding this last slide, what do you mean with this CP symmetry can always be defined?
Yeah. Good. Thank you for asking. So, when you do parity, as I said, you take the left-handed field and transform it into a right-handed field. And imagine that I define a theory that only has left-handed fields, right? And I want to test whether it's a parity invariant. If I make a parity transformation, it transforms the field into one that doesn't exist in the theory because there's no right-handed fields in the theory. So I can't even define it. And the same thing happens with charge conjugation. And that's basically because the charge conjugate of a left-handed field, a spinor which is left-handed, is also a right-handed field. So if you only had left-handed spinors and you make charge conjugation, you also have the same type of problem. So theories which only have left-handed spinors or only have right-handed spinors, you can't even define you can't even ask the question properly of whether the Lagrangian is invariant under parity or under charge conjugation. However, because both charge conjugation and parity change left-handedness into right-handedness, if you apply them both in succession, you end up mapping left-handed fields again into left-handed fields. And then you can show that that's always the case, that CP always kind of closes within this set of fields in your theory. And so you can always define it. The weak interactions of nature that produce beta decay, that I will talk very briefly about tomorrow, they were very surprising to show parity violation back in, it was discovered in the 50s. I think. And the way we understand today how parity is violated in nature through weak interactions is precisely because we can't even define parity in weak interactions, because it's only there's some fields that come in that are only left-handed, and that interact weakly. Weakly meaning under the weak interactions. And so if you try to define parity, you can't even define it. So it's just that bad. It's people say it's maximally violated because you can't even define it. However, you can define CP, and for a long time there was a question, well, is CP a good symmetry or not? And that was a completely separate question.
Okay, and since CPT is always a symmetry.
Yeah. Ask me later. I'll be happy. Yeah.
Thanks.